Welcome to the deep dive. We've got a really fascinating figure to explore today, Henri Poincaré.
Yeah, a really, really interesting guy.
I mean, just the sheer breadth of his work, right? Mathematician,
Oh, yeah.
theoretical physicist,
Mm.
philosopher of science.
And often called, like, the last polymath, right?
Yeah.
Because he really did make significant contributions across so many different fields.
And that's kind of what makes him so interesting for us, right?
Exactly.
Because we're not going to be doing a deep dive into, all of Poincaré's work in mathematics or physics, but more into his philosophy.
Right. But what's especially interesting about his philosophy is that it really comes out of his scientific practice.
Yeah.
So it's not like armchair philosophizing.
No.
It's really grounded in the work he was doing, the scientific debates of his time.
And you can really see that with the influences, right? I mean, we see people like Ernst Mach,
Yeah.
James Maxwell, Hermann von Helmholtz.
But then also, like, the philosophical figures of his time, right?
Right.
So you've got Émile Boutroux, Jules Lachelier, William James.
And kind of this backdrop of neo-Kantianism.
Yeah.
But one thing we should say right at the beginning, I think, for, philosopher listeners, is that when Poincaré uses kind of this Kantian vocabulary, it often doesn't mean quite the same thing that it meant for Kant.
Right.
So there is this familiar language, but you can't just assume a direct equivalence.
Yeah, for sure. So it's really important to be aware of that. And I mean, Poincaré wasn't some isolated figure either.
No.
He was really right at the center of the French philosophical scene. He even collaborated with Émile Boutroux on an edition of Leibniz's Monadology.
Yeah, and when you look at Poincaré's work, I mean, he's constantly publishing in the Revue de Métaphysique de Morale.
Oh, yeah.
And he's a major figure in organizing these big philosophical events. I mean, we see him at the Descartes Centenary. We see him at the International Leibniz Project.
You're right. So he's really a key figure in the philosophical debates of the time.
So when we look at Poincaré's philosophy, I mean, what are some of the core debates that he was engaged in that we are going to sort of try to get at in this deep dive?
Well, I think the two things he's probably most known for are, first of all, his critique of logicism.
Okay.
And then his theory of geometric conventionalism.
Okay.
But I think we can even place those debates within a kind of broader philosophical project.
Okay.
Which I think was really an attempt to reconstruct how we understand scientific theories. And I think he was really navigating between, on the one hand, you have a kind of traditional realism.
Right.
Where we think our scientific theories are somehow directly mirroring reality. And then on the other hand, you have various forms of anti-realism.
Yeah.
Where we question that connection.
Right. So let's start maybe with how Poincaré saw the structure of science itself.
Okay.
What was his vision of how scientific knowledge was sort of architecturally put together?
So, in his book, Science and Hypothesis, which is really one of the best places to go to understand this, he presents what we might call a hierarchical view of the sciences.
Okay.
He places arithmetic at the foundation, and then he builds geometry on top of that.
Okay.
Then physics, and then finally the kind of special sciences, the other sciences on top of that.
So how does that dependency structure actually play out in Poincaré's view?
So Michael Friedman, the philosopher of science, I think gives a very interesting interpretation of what Poincaré is doing here.
Okay.
Which I think is helpful, which is that he's saying each level in this hierarchy somehow presupposes the validity and the applicability of the levels below it.
Okay.
So, for instance, Friedman uses the example of Newton's law of universal gravitation.
Okay.
And he's saying the very discovery of that law was contingent on, Newton's prior establishment of the laws of motion,
Right.
and then also Euclidean geometry.
Right. You need the geometric framework.
Right. And so you can't have the laws of motion without already having some framework for thinking about space and movement, which is geometry.
Right. Right.
And then geometry itself relies on the theory of mathematical magnitude for the possibility of measurement.
Right.
And then, of course, underpinning all of that is arithmetic.
So when we say mathematical magnitude, that's sort of this intermediate step between arithmetic and geometry.
Exactly.
And that's where you get the idea of measurement coming in, right?
Right.
Which is central to geometry.
Yeah, exactly. And so, I mean, a key part of the theory of magnitude is the possibility of indefinite repetition.
Right.
Which then connects to the idea of mathematical induction, which Poincaré sees as so central to arithmetic.
So what you're saying is that for Poincaré, mathematics isn't just a kind of tool that's used by physics,
Right.
but it's actually a prerequisite even for formulating the physical laws that we discover through experiment.
Exactly. Yeah.
That's a strong claim.
Yeah. Yeah, it is. I mean, he explicitly says the objective of mathematical theories is not to reveal to us the true nature of things,
Yeah.
but to coordinate the physical laws that experiment reveals to us.
Right. So there's no reality behind the math, in a sense.
Yeah, he's not a Platonist in that way.
But rather the math allows us to express these physical laws that we wouldn't even have the language for otherwise.
Exactly.
Now, we did see some critiques of this hierarchical model. I'm thinking specifically of Dunlop.
Right.
What was the main thrust of his criticism?
Well, his worry was that this hierarchical model was actually a kind of reductionism.
Okay.
So his worry was that Poincaré was saying, for instance, geometry was nothing more than arithmetic.
Okay.
But that's actually, I think, not really what Poincaré was saying.
Okay.
It's not that geometry is, identical with arithmetic.
Yeah.
But in order to do geometry, you still have to rely on arithmetic.
Okay.
Right? So you need that foundation. And then you're adding something new in each level.
I see. So it's more like a cumulative process, right?
Exactly.
Where each level builds upon the previous one, but introduces new elements at each stage.
Exactly.
And then, of course, when you get to physics, you're introducing the empirical content.
Right.
Which you can't reduce to the purely formal structures of math.
Yeah.
Poincaré uses this really nice image, I think, of concentric circles.
Oh, yeah.
So arithmetic is this innermost circle.
Yeah.
And then each science that comes after encompasses that previous one.
Right.
But it adds its own distinctive features.
Right. So the lower levels are necessary, but they're not sufficient.
Right.
For the higher level sciences.
Okay, so within this kind of structured view of science, Poincaré distinguishes between different categories of hypotheses. And it seems like there are 4 main types that you've pulled out of his work.
Yeah, and I say pulled out because he doesn't actually present them all neatly in one place.
Right.
So it takes a little bit of work to bring them all together. But I think we can identify these 4 categories. So we have, first of all, verifiable hypotheses.
Okay.
We have what he calls indifferent or neutral hypotheses.
Okay.
We have natural hypotheses.
Okay.
And then apparent hypotheses.
All right, so let's break those down a little bit for the listener.
Okay.
So verifiable hypotheses, it seems like those are kind of the standard scientific claims that we actually test against experience.
Right, exactly. So these are, what we might think of as the kind of bedrock of natural science.
Okay.
But what's interesting about Poincaré, and I think this is really important for understanding his philosophy, is that he doesn't think that science is just made up of these verifiable claims.
Right.
He's really trying to find this middle ground, I think, between a kind of pure empiricism and pure rationalism.
Okay. And then we've got these indifferent hypotheses. So what role do those play in his philosophy?
So these are more about the kind of underlying mechanisms that our theories posit. Okay. So often they're going to take the form of, some kind of ontological model.
Okay.
And the point about these is that you can often substitute one indifferent hypothesis for another without actually affecting the empirical predictions of your theory.
Okay, I see. So you could imagine, 2 different models of how something works, but if they make the same predictions, then in a sense it doesn't really matter which one you pick.
Right, exactly. So Poincaré gives the example of heat propagation.
Okay.
So we might have different models about what's going on at the molecular level.
Right.
But as long as the overall predictions about how heat flows are the same, it doesn't really matter empirically which model we choose. And so Poincaré thinks these are useful tools for kind of guiding our thinking.
Yeah.
But ultimately, they're unverifiable.
Okay.
We can't actually test them directly.
Okay. So natural hypotheses. These seem to be the kinds of things that are necessary for science to even get off the ground.
Yeah.
But they are themselves not directly testable.
Right. So these are the kinds of almost unavoidable assumptions that we have to make when we do science. So, for instance, the assumption that the influence of really distant bodies is negligible.
Okay.
Or the assumption that for small motions, we can use a linear law.
Okay.
Or the principle of continuity between cause and effect.
Yeah.
Poincaré also includes the conditions that are imposed by symmetry.
Okay.
So he thinks all of these are kind of foundational for constructing our scientific theories.
Yeah.
But we can't test them directly.
Okay. And then finally, we have these apparent hypotheses. And these seem like they're the most philosophically interesting.
Right.
Because these are things that look like they're making factual claims about the world, but actually they're more like definitions or conventions.
Exactly. And so the best example of this for Poincaré is metric geometry.
Okay.
So he thinks we often mistake statements about the geometry of space to be discoveries about its inherent nature. But actually what we're doing is we're adopting certain frameworks or conventions for describing and organizing our experiences.
Okay, so let's dig into the levels of the hierarchy a little bit.
Okay.
Starting with arithmetic. You mentioned the centrality of mathematical induction for Poincaré.
Yeah, absolutely. So the principle of recurrence or mathematical induction, Poincaré sees this as a synthetic a priori principle.
Okay.
And it's interesting because he thinks it's so self-evident that we can't even conceive of its negation.
Okay.
So it's really fundamental for him to commiserate the possibility of proving general statements about all numbers.
So where does this kind of certainty that mathematical induction provides, where does that come from for Poincaré?
So he thinks this is rooted in the mind's fundamental capacity to conceive of the indefinite repetition of an operation.
Okay.
So it's based in this kind of cognitive ability that we have. And this is very different from, the principle of induction in the natural sciences.
Right.
Which only yields probabilities.
Right. So there's a really fundamental epistemological distinction for Poincaré.
Exactly.
Between mathematical induction, which gives us certainty, and scientific induction, which only gives us probability.
Right.
Okay, so let's move on to geometry. This is where this idea of conventionalism really comes into play.
Yeah, exactly.
So how does this challenge traditional views of geometric truth?
So Poincaré famously argued that metric geometry is neither a matter of a priori intuition nor a purely empirical discovery, but rather a matter of convention.
Okay.
But, and this is important to note, he doesn't think these conventions are arbitrary.
Okay.
He emphasizes that they're guided by experience.
Okay, so the fact that we have these consistent non-Euclidean geometries shows that we can't just know the geometry of space through some kind of a priori reasoning.
Exactly.
Which seems to be challenging Kant directly.
Yeah, exactly. I mean, and then also because our experience of space is always mediated through our experience of bodies, and the relations between bodies, rather than a direct apprehension of space itself, Poincaré says we can't empirically determine the true geometry of space either.
Right.
And so what we're really doing when we talk about the geometry of space is we're choosing a convenient framework for describing our experiences.
Okay. And this is where this idea of sensible space comes in.
Right.
So what is sensible space as opposed to, kind of geometric space?
So Poincaré thinks our initial sensory experience of objects, this is going to be a kind of complex interplay of motor and visual impressions that are not inherently spatial or metric.
Okay.
Right. So to make sense of these sensations, and especially the sensations that arise from our own bodily movement, we develop what he calls sensible space as a kind of fundamental category of our understanding.
So this sensible space isn't the same thing as physical space.
Right.
And crucially, it doesn't have a metric.
Yeah.
There's no pre-given notion of measurement in sensible space.
Exactly. It functions more like what he would call a natural hypothesis. So it's a kind of necessary framework for orienting ourselves in the world.
So how do we go from this non-metric sensible space to the metric geometry that we actually use in our scientific descriptions?
So this is where group theory comes in.
Okay.
So Poincaré says we introduce a metric structure to sensible space by employing the conceptual tools of group theory.
Okay.
So these groups give us a formal language for reasoning about the muscular sensations that are associated with movement.
Okay.
So we can choose a particular group or a subgroup of that group, which corresponds to, Euclidean geometry or Lubitschewskian geometry or Riemannian geometry, to serve as a framework for describing spatial relations.
Okay, so why do we typically choose Euclidean geometry? I mean, is that just another arbitrary convention out of all the possibilities that group theory offers us?
It's not totally arbitrary. Poincaré actually gives a criterion for guiding this conventional choice.
Okay.
So he says we should choose a geometry that has an invariant subgroup of translations. So this means that all displacements are interchangeable.
Okay.
And it turns out that only Euclidean geometry satisfies this particular criterion. So it is a convention, but it's a convention that's guided by these considerations of simplicity and convenience.
Right. So in the language of mathematics, it leads to, fewer terms in your equations, simpler equations.
Exactly.
Okay. So we've got arithmetic, which provides the foundation through mathematical induction.
Yeah.
We've got geometry, which we construct upon that, using these conventions that are informed by experience and kind of formalized through group theory.
Yeah.
So how does natural science or physics fit into all of this?
So in natural science, Poincaré is really focused on what he calls verifiable hypotheses.
Okay.
So these are the empirical laws of mechanics that we arrive at through experiment.
Okay.
And for him, what makes an experiment significant is not that it isolates a single fact, but that it allows for generalization and prediction. And this very process of generalization, he thinks, presupposes a belief in the underlying unity and simplicity of nature.
But he also warned that experience is theory-laden, right?
Well, absolutely, yeah.
So how does that affect the kind of supposed verifiability of these hypotheses?
So Poincaré's point is that any experimental result can be generalized in a multitude of ways.
Okay.
And the particular generalization that we adopt is always going to be shaped by our pre-existing ideas.
Okay.
And the theoretical frameworks that we're working with. So even these supposedly purely empirical generalizations have a conventional element to them.
Okay.
But it's important to note, he's not saying that natural laws are just definitions, like some of his contemporaries were suggesting.
Okay.
He's trying to find this middle ground.
Right.
Okay, and so how does mathematics, specifically the language of differential equations, fit into this picture?
Yeah.
So Poincaré sees differential equations as absolutely indispensable for capturing the complexity of physical phenomena and for unifying different areas of science. He even goes so far as to say that physical laws are essentially differential equations.
Wow.
So they describe how the present state of a system determines its infinitesimally subsequent state.
Okay.
And you can even think of like the law of inertia, that very formulation, that very concept relies on this pre-existing framework of differential equations.
Okay.
So you couldn't even have that concept without the math.
So within mechanics itself, there's also this kind of hierarchical structure of how we arrive at knowledge.
Yes.
You're moving from just our raw experience to these fundamental laws.
Yeah. So we start with these complex phenomena that we observe through experience. Then we dissect those into simpler elementary phenomena through experiment.
Right.
Then we use empirical induction to generalize these findings into elementary facts.
Okay.
And then finally, we use the language of differential equations to formulate the laws, the verifiable hypotheses. And then some of these laws, the ones that are very well established and successful, those get elevated to the status of principles.
Okay, so these principles of mechanics, like the laws of inertia, acceleration, he's saying those are also conventions, but they're conventions of experimental origin.
Exactly.
That's an interesting idea.
It is, yeah. So they're not arbitrary.
Right.
They're rooted in a huge body of experimental evidence.
Right.
But their function in the theory is more like definitions.
Okay.
They're defining basic terms. And so in that sense, they're not really subject to experimental disconfirmation in the usual way.
I see. So they become kind of preconditions for doing science.
Exactly, yeah.
Okay, now, and these indifferent hypotheses, they kind of make a reappearance here in physics, don't they?
Yes, exactly.
So what's their role in physics?
So here they're going to be the kinds of assumptions that we make to facilitate calculations.
Okay.
So they can be psychologically helpful, they can be pedagogically useful, but they're not actually making definitive claims about what's real.
Okay.
And so you can actually change them or even discard them without affecting the actual predictions of your theory.
Okay.
And I think this really points to Poincaré's structural realism.
Okay, so this is the view that the essential content of our scientific theories isn't necessarily the entities that they posit, but the relationships, the structures expressed by the laws, which tend to endure.
Exactly.
Okay.
And so there's this interesting kind of methodological parallel that we see between induction, these apparent hypotheses or conventions, and the verifiable hypotheses, which is that they're all ultimately informed by experience.
Right.
And they all involve some kind of pre-existing conceptual framework or structure.
Okay, so now let's turn to the philosophy of mathematics, and specifically Poincaré's contributions there. And in particular, I mean, he has this famous critique of the logicist program.
Right.
So this was the attempt to ground all of mathematics in logic. What were his main objections?
So he had two main objections to logicism. First of all, he thought that logical inferences alone are insufficient for genuine mathematical reasoning.
Okay.
So he thought there was something more going on than just applying the rules of logic. And secondly, he was really worried about the paradoxes that were being discovered at the time.
Okay.
And so he argued that we should avoid impredicative concept formation.
Okay, so these are definitions that define something by referring to a totality of which that thing is a member.
Exactly.
Okay. So these arguments were really targeted at those who are trying to establish logic as the foundation for all of mathematics and set theory.
Exactly. So we're thinking of people like Cantor, Peano, Frege, Russell, Zermelo, Hilbert.
I mean, that's basically everyone, all the big names.
Yeah.
And it's interesting. He was initially somewhat interested in Cantor's work on, function theory.
Right.
But he really rejected Cantor's foundational work on actual infinity. So now there seems to be this debate among scholars about what the real nature of Poincaré's disagreement with the logicists was.
Yeah.
Was it just that he didn't find logicism psychologically convincing? Or was there a deeper epistemological objection about how we actually come to know mathematical truths?
Yeah, that's a really interesting question. So some commentators, like Boutroux and Goldfarb, they suggest that Poincaré's main worry was just that logicism wasn't psychologically convincing. It didn't give him this sense of certainty.
Right.
But then others, like Detlefsen and Heinzmann, they argue that Poincaré's disagreement went deeper. It was about the nature of mathematical knowledge. And it's interesting because Poincaré himself said he couldn't neatly separate logic from psychology, or even epistemology from psychology. Although we should say his use of psychology wasn't quite the same as what we mean by psychology today.
Right.
For him, it often included this element of mathematical understanding, which included kind of the historical evolution of mathematical concepts. Which he contrasted with just giving a purely formal, logical presentation of results.
So this is where intuition comes in, right?
Yes, exactly.
So for Poincaré, intuition plays a really important role in mathematics, not only for discovering new ideas, but also for justifying those ideas.
Exactly. And he thought that what he called pure intuition was necessary to provide the foundation for mathematical induction in arithmetic. And he even distinguished between different forms of intuition. So we have the intuition that's derived from our senses and imagination. We have the generalization that we achieve through induction. And then this kind of fundamental intuition of pure number.
Which gives us the axiom of induction.
Exactly. And so he completely disagreed with this idea from the logicists. That you could prove all mathematical truths just through logic without any appeal to intuition.
He thought that true mathematical reasoning involved seeing a specifically mathematical connection rather than just applying, topic-neutral logical inferences.
Exactly.
And he called this a local conception of reasoning.
Yeah.
So the idea that things like induction are really specific to particular domains of mathematics, like arithmetic.
Yeah. And for him, like, if you see a gap in a mathematical proof, that's not just a logical error. It's a sign that there's something missing in our mathematical understanding. So we really need to fill in that gap.
So if Poincaré wasn't a fan of this kind of strict formalization in the logicist sense, what did he consider to be the essential elements of mathematical rigor?
Well, I think for him, rigor was really about condensing the information that's in the premises down to the conclusion in a way that we can intuitively grasp. And so he drew on Mach's principle of the economy of thought. And he also emphasized the role of language in conveying mathematical ideas. So for him, language wasn't just a passive tool for expressing mathematical truths that were already there. It actually played a really important role in structuring our understanding and harmonizing our mathematical ideas.
So how did he explain the logical paradoxes that were being discovered, at the turn of the century?
So he thought that these were due to what he called an abusive use of intuition. When we're dealing with very abstract entities. And he saw this as stemming from a kind of Platonist view of mathematical objects.
So the idea that there are these objects out there, and we're just trying to describe them.
Right, exactly. So his worry was that if you intuitively posit the existence of these sets without imposing any restrictions on how you define them, then you're going to run into contradictions. And Poincaré was increasingly skeptical of Platonism.
Okay.
He thought intuition was more about our ability to follow rules,
right,
to apply procedures, than about representing these pre-existing objects.
Okay. And this is where his emphasis on predicative definitions comes in, right?
Exactly.
He wants to avoid these vicious circular definitions
Yeah.
that seem to lead to the paradoxes.
Exactly.
So he aligned himself with Russell's vicious circle principle.
Yeah. Yeah.
Which basically says that, if you're talking about all members of a class,
right,
that thing itself can't be a member of that class.
Right, exactly.
So Russell developed ramified type theory as a way to formally deal with this.
Yeah.
Poincaré's approach was a little less systematic.
Yeah, he was more reacting to specific instances where non-predicative definitions were being used.
Okay.
Like in the proof of the fundamental theorem of algebra.
So there was this debate then between Poincaré and the logicists about how to formulate a principle of predicativity that would avoid the paradoxes, but not be too restrictive.
Right.
And it seems like they never really came to a completely satisfactory solution. Yeah.
Using just these informal methods.
Right.
Now, Brouwer comes along and famously characterizes intuitionism and formalism as the two main schools of thought in the foundations of mathematics.
Right.
Where does Poincaré fit into this picture?
So Brouwer himself actually saw Poincaré as representing the intuitionist side, as opposed to Hilbert, who represented the formalist side.
Right.
But, Brouwer also criticized Poincaré for not fully separating the language of mathematics from these mental constructions that the intuitionist thinks actually constitute mathematical objects.
Right.
So Poincaré, unlike Brouwer, thought language played a really important constructive.